If you're deaf or hard of hearing, a noisy room isn't just loud. You miss what is said and what happened around you. Speech and environment, sounds both carry context. That's the problem we chased at the 24-hour hackathon in October 2025, LA Tech Week at USC ISI. We are a team of 4 people. Everyone contributed to the shared code base. I led the development, teammate owned the README, design, and the on camera demo, one repo for all the 4 merges. It was our first build on Vision Pro. Before Aura, we shipped a tiny proof of concept. Say red, the space turns red. Speak louder, it grows. This proved the deploy microphone speech and spatial rendering before we built the real app. This video is the system design story of what we tried, what we cut, and what actually shipped in the hackathon. Aura runs on Apple Vision Pro, live speech translation plus environmental sound classification entirely on device. The first decision, everything stays on the device. No cloud speech API, no uploading the audio. The hackathon temptation is to cheat. We send the audio to a network recognizer when on device struggles, which is faster to demo and often more accurate. We rejected that for 2 reasons, privacy and latency. For accessibility, unpredictable delay is as bad as a wrong text. So we committed to Apple's on-device speech framework, ASAP Speech Recognizer, with no network fallback in our code. To maintain zero external dependencies, we made a trade-off of using speech models per language. User would need the language pack installed in order to use the product. We did not train any machine learning model. We chose to integrate Apple ML model instead of training a custom. Apple had recently shipped their strong on-device models, speech for transcription and sound analysis for environmental classification, which is good enough for the product idea. We selected the left path, which meant collecting the data, label, train, export the core ML, and debug, which is a multi-week project. We only had 24 hours in the hackathon. The job was integration engineering, one microphone tab feeding into 2 different consumers, speech transcription, and caption segmentation using sound analysis. And finally, an UI that maintains 90. If we'd spent the hackathon training the model, we would have no working app. We traded the ML research for a working accessibility prototype and eventually got second place in the hackathon. We integrated the Apple's model. The engineering story is everything around them. One microphone tap on the AV audio engine input node. So every buffer flows through a single install tap callback. This one tap fans out to Apple's speech framework for transcription and sound analysis for environmental classification, which meant parallel on-device consumers. Heavy work never runs inside the tap, so we dispatch a serial queue com.aura.analysis queue so the analysis can't stall the real-time audio. Environmental sounds flap labels. We gate on 0.6 confidence and throttle updates to 0.25 seconds. I added 7 recognition language in the picker, so the user can switch without restarting the whole engine. Live English caption and whisper detection. Both pipelines were working in the same session. Speech recognition returns a formatted string of one continuous term. No pauses, no sentences, no structure. During a live conversation, this becomes an unreadable wall of text on the screen. First layer, temporal segmentation. When the speaker pauses for longer than 1.1 second, we can treat that as a new utterance, which is a breath between thoughts or different speakers. Second layer, grammatical splitting. Abbreviation like doctor, an example, strain tag. so we can only break on real sentence boundaries. One utterance in and clean sentence chip out. Before just one plop, after an utterance to sentence chunks that you can actually read while someone is talking. The two-layer split fix the readability and it holds with multiple speakers. Reality Kit runs at 90 Hz. Hooking captions via view attachment means SwiftUI would run re-layout on every frame. Layout cost tied directly to the render loop. We mark this path. Off-screen bake, we render the caption in SwiftUI, snapshot to a texture and composite on a lightweight quad in the scene. This debounces rebakes 200 milliseconds, so we don't thrash the GPU. Same caption content, different render path. Per frame layout jitters the HUD. The bake texture stays pinned to the. What we actually shipped in the demo: a 2D heads-up display overlay, not the full world space texture part. Speech and sound delegates fire on the background threads, not the main actor. ML results arrive while the tab keeps running on the audio thread from chapter 3. Any published property that derives SwiftUI must mutate on MainActor. We wrap captions update in task MainActor so the panel refreshes safely. That's why the live caption can refresh on screen while classification keeps streaming. UI works hops onto the main. The tab never waits. Early on, we tried to pin each sound to the direction it came from, markers in the world where the audio seemed to originate. First problem: Vision Pro gives direction from the mic, not the exact coordinate. The pin is a guesswork, which meant drift and feels wrong. Second, for accessibility, an urgent sound behind you might never enter your field of view. A baby crying pinned outside your gaze is a missed. So we pivoted to an Iron Man style heads-up display. Caption and sound labels are on the panel that stays in the view. Head relative, not world hunted. That's what's in the demo shows. We still compute the azimuth direction in the audio path for analysis, but we don't ship it in the directional markers in the UI. Separately, we built a spatial heads-up type prototype. Texture were baked into the Swift UI in Reality Kit, and this is what we demoed in the. It was a hackathon prototype. One user, one headset, and no benchmarks. We demoed the live captions and sound alerts qualitatively. We did not measure any thermal, battery, or latency as we would have if it was a production. The same core pipeline could grow into a product. Local bundles in CDN, observability, multi-user fleet metrics. This means the same core pipeline but different ops envelope. We never claim any latency percentage, production user metrics, or benchmark artifacts. The demo is a proof of concept. To summarize, we built one tab that serves on-device speech and sound analysis, caption and alerts in view. This is the pipeline we built in 24 hours. Links are in the description. The GitHub, the full demo video, and the short demo video. Finally, we won the second place in the hackathon.